Hello, I'm Annie Graham Larkin, Executive Director of the Bisbee Mining and Historical Museum. Welcome to Unraveling the Secrets of Bisbee's famous turquoise occurrence with Dr. Mark Pecha. Thank you to our members and donors who enable the museum to provide free online programming and fulfill the organization's mission to discover history, explore Bisbee's past today. To learn how you can assist the museum in supporting its mission and programs by becoming a member or donor, please visit bisbeemuseum.org. And today is the final day of the Bisbee Mining and Historical Museum's Vintage Turquoise Jewelry Show and Sale. The sale will offer one-of-a-kind antique Native American jewelry ranging from earrings to squash blossoms. Don't miss this opportunity to find a unique gift for someone special in your life or to treat yourself to an exceptional piece of jewelry. This event at the museum will end at 4 p.m. today and is included with regular museum admission. All right. Dr. Mark Pecha is the research manager for the Arizona Laser Center within the Department of Geosciences at the University of Arizona. Mark completed both his MS and PhD at the U of A and specializes in geochronology, geochemistry, and the plate tectonics of North America. Mark has managed the ALC for about 16 years, and during his time has co-authored over 60 peer-reviewed geological publications. He is passionate about the mineralogy of Arizona, particularly Bisbee, he has good taste, and collects mineral specimens that tell a geological story. And if you would like to ask questions during the program today, please type your question into the Q&A chat box, and we'll gather those questions to share with our speaker after the presentation. Also, a link to the recording of today's program will be sent to all of our Zoom registrants later today. And with that, I'd like to welcome you, Mark. Thank you so much for joining us today.
You bet, Annie. Thanks for joining or having me on the program. Excellent. Well, we'll jump right into it, and as you can see from the title, we're gonna talk a little bit about turquoise today. But before I begin, I just want to give a shout out to the reason that I'm here today working on Bisbee minerals. And it's one of my mentors, Richard or Dick Graham, as most of you knew him. Um, is one of the reasons that I fell in love and have the passion for Bisbee mineralogy that I do. And Dick passed away a few years ago. The top picture is a tribute case that we did for Dick, a friend of mine. There were a whole bunch of cases that year at the Tucson Gem and Mineral Society, um, just to repay all the tools that he's given me and my colleagues over the years. So um, as I go through the presentation today, a lot of it, all the basic geology and background for the exploration that we've done comes from all the work that Dick and his two sons have done, Richard and Doug. And so the publications at the bottom there here are just some of the ones that I would refer you to down the road if you like what we talk about today. I started with this one on the left, the 1983 MinRec from Bisbee, and I think I've gone through 4 or 5 different copies of it as I wear them out. So I wish the same on all of you. So before I begin, I just want to give a shout out to my collaborators, Richard Graham IV, Doug Graham. Uh, those of you who are familiar with Bisbee mineralogy, they need no introduction. But Dr. Jason Kirk is somebody I work with here at the U of A. He has a research lab just very similar to mine, but more focused on ore minerals. And then Gabe Sanchez. Gabe's was a student that worked on the turquoise, part of the turquoise I'm going to present today, and was instrumental in the findings that we've come. In fact, Gabe has graduated since and is now part of the Arizona Laser Center that I run. So we're going to talk about provenance of turquoise, particularly Bisbee. But why is the provenance of gemstones and minerals, why is it important? There are a couple sides to it. One comes from the mineral and lapidary and gemstone perspective. And as a mineral collector, I specialize in a certain locality. I want to know that the way that it's labeled and what I can learn from it, that it's correct. But from the lapidary and gemstone perspective, also the price of these, the jewelry and minerals that whether it's turquoise or something else, price is certainly affected by locality and scarcity. So that's a huge consideration. But the reason that I'm so passionate about learning more about these minerals is the scientific perspective. As far as turquoise is concerned, there's a huge archaeological significance. Understanding prehistoric mining activities, understanding the trade routes. If you find or if you're learning about a an archaeological find and find turquoise, you want to know, hey, what are the trade routes? Where was this turquoise mined? Is it from Morenci? Is it from Kingman? Is it from Mexico? That sort of thing. And then there's also the geologic significance. As Annie mentioned, I like to collect minerals that tell a geologic story. And some like turquoise, can tell something about tectonics or paleoclimate even, or ore bodies and ore deposits. So we're going to examine all these things today while we talk about turquoise and have some fun and show some pretty pictures as well. The outline for today's talk is just a little bit of basic geologic background, learning how these copper deposit formed in Bisbee and the mineralization. Also, we'll talk about the history of turquoise mining in Bisbee. And then we'll talk about the work that we've done here at the University of Arizona for turquoise provenance determination. So for those of you who don't know where Bisbee is, Bisbee sits in the far southeastern corner in Cochise County, so southeastern corner of Arizona. And today, that bottom picture here is shows you what Bisbee's all about today. There are lots of shops. It's become an artist, I don't know if you'd call it an artist retreat, but an artistic community for sure. There's some restaurants, and spending the day in Bisbee is a wonderful day or the weekend. To me, this is what I see when I go to Bisbee on the right, all these different mines. I think about the ore deposits. I think about the mining history, the lavender pit that you drive by and can't stop, or you can't drive by it without stopping and getting out of your car and looking because it's so exciting. So that's what we're going to talk about today. And to learn more about the turquoise, we first need to understand what is the deposit at Bisbee or the deposits and how were they formed. And so this cartoon here on the left is is really just a cartoon, if you will, from Kirkham and Sinclair in 1995 of what a porphyry copper system looks like. And so during the Jurassic time, that's when the Bisbee turquoise or Bisbee deposits formed about 200 million years ago. There was subduction along the western coast of North America, where the oceanic plate was subducting underneath North America, and there was a line of stratovolcanoes, and there would have been a stratovolcano over where the Lavender Pit is today, roughly. And this sort of shows you what it would have looked like. There are a series of intrusions, this pink body coming up, that are part of the Sacramento stock. And during the emplacement of the Sacramento stock, there were lots of hot waters flowing and circulating and carrying some of those intrusions. Also, with the hot waters, carried minerals. And the neat thing is the minerals and hot water reacted with those blue layers that you see here on the left. Those would represent the Paleozoic limestones that sit above more unreactive rocks, which are the Pinal schist, which would have been the country rock. So the fact that these intrusions entered where they did, carried the minerals that they did, and interacted with these very reactive limestones. Certain units in the Paleozoic section of limestones was very reactive. It created lots of ore bodies. Well, today, if you look at the cross section to the right, this is all the way back from Phelps Dodge in 1938. They recognized hey, these ore bodies are related to intrusion, this intrusion, and today the carapace, that volcanic carapace, is gone, and what we're left with is some sort of erosional surface, the intrusion, and then the reactive Paleozoic limestones that hosted a lot of replacement style ores. The map on the left here, just looking down upon Bisbee, is from Ransom 1904, and they also Ransom did a geologic map, and this orange body represents from map view what the intrusion would have looked like. Well, if you come over to this top diagram to the right, that intrusion is represented in the stippled pattern where my mouse is. And if you notice, there's a big fault right here, and it's called the Dividend Fault. And the southwestern side of that fault dropped down more than 1,000 feet, multiple different times it's moved. But that drop down of the fault allowed us to preserve all the beautiful ore bodies and minerals that are preserved in Bisbee, including where the turquoise formed. So all these black shaded bodies, those are the ore bodies that wrap around this intrusion. So it's clear that you can see that the ore bodies in Bisbee are related to the igneous intrusions in the area and the hot waters that circulated during the intrusions. And then they percolated out into discontinuous, often unconnected ore bodies along these other faults. And all those were mined by different shafts and mines throughout Bisbee for the last 100 years up until about 1975. So the first mineralization that occurred in Bisbee, it's called hypogene mineralization, and that comes with these intrusive complexes. So there were four different intrusive complexes that came into the area. The first was a quartz porphyry. There was lots of pyrite that came with that intrusion, but no copper. It wasn't until the younger porphyry, also about 199 to 200 MA, this happened. And it's during that stage of intrusion that we introduced copper into the system. And there are lots of what are called hypogene minerals or primary minerals that come with these hot waters. They're not very attractive to look at typically. And I put stars next to the important ones as far as we're concerned. The most important ones, they're all important. But boronite, a copper sulfide, chalcopyrite, same thing, pyrite as well. No copper in pyrite, but it contributed to the generation of acidic fluids during supergene enrichment. So along with these four intrusions, there were four pulses of mineralizations. Each of the pulses of mineralization brought a different suite of minerals. And all this has been figured out by previous researchers. This is none of the new research that we've done, but thanks to all the people that did it before us, we certainly know about it. And then it's the oxidation of these hypogene minerals. So the two pictures at the top right show typical hypogene mineralization where you have quartz veining and not very exciting rocks, lots of disseminated sulfides, so chalcopyrite, boronite, either along veins, edges, and salvages, or disseminated through the rock. But it's not until that rock is uplifted, exposed to oxygen and air, that you oxidize these sulfides. And when you oxidize the sulfides, a reaction like this happens. So if it's pyrite, iron sulfide mixed with water and oxygen releases the iron and sulfate and positive hydrogen ions. Well, this iron is typically left behind. And you see that at Bisbee. It creates those beautiful red hills. So it did it at Morenci here in this photograph by Taylor in 2011. This red here is hematite leached cap. So there are oftentimes oxide ores in there, but most of it's just overburden on these deposits. On the right is a picture of the Lavender Pit and part of the Cochise deposit at Bisbee, and you see all the red stained rocks. That's because the primary hypogene ore was uplifted, oxidized, and then reacted And what's left behind is the iron, and then the copper is percolated down to form different things like calcite, copper sulfide, or the beautiful minerals that we're talking about, and we know about Bisbee, all the malachite, the azurite, and the turquoise, in addition to about 160 other supergene minerals at Bisbee. So the really neat thing is they've recognized four distinct events where this erosion has happened. So remember, the ore deposit itself formed 200 million years ago. But since then, there have been four episodes in different parts of the district where they've experienced this supergene alteration and mineralization. And that's one of the reasons we have such a wonderful mineral heritage at Bisbee, because all this time that goes on and each of these supergene cycles gives us an opportunity to form minerals. So there was one that happened right after the emplacement of the ore. So this would have happened late Jurassic, early Cretaceous time. Then there was another one in mid-Cretaceous about 110 million years ago or so. And that's when the dividend fault was very active, dropped more than 1,000 meters, and exposed this hypogene mineralization. Then there was a later one in late Cretaceous during Laramide tectonism. And each of these parts of the region, I won't get into this in depth. If you want to learn more, come take one of our classes at the U of A, and we'll get into this in depth. But for our purposes, just realize a lot of time has gone on, and different parts of the district have been eroded at different times and to different extents. The neat thing is you can actually tie different mineral specimens and how they grow and to these different events. And so the top section, this is a malachite pseudomorph. This top photograph where my mouse is a malachite pseudomorph after azurite from the 1300 level of the Campbell shaft. And the idea is that those formed during that initial late Jurassic, early Cretaceous time frame. Others, like that bottom photograph, you can see solution lines where part of this azurite from the Czar mine, this is part of the Graham collection, part of it grew in a subaqueous environment and part of it grew in a subaerial environment. So there must have been some water level right there at that line. And we could tell these things and learn these things. So this is what gets me excited. And what really gets me excited are the beautiful minerals that are produced from this supergene mineralization and alteration. Here's just a sampling of some of my favorite specimens. The top left is an azurite on malachite, beautiful azurite rosettes. Most of these that are pictured here, at least the top row, are all from the late 1800s. This one's from the Czar mine. The next two are two malachite specimens that are both in the Smithsonian Museum collection. Those are part of James Douglas's original mineral collection, malachite stalactites. Or here, this second one, it's almost like a flower that actually formed at that same surface between a subaqueous and a subaerial environment. The one to the right, part of the Beckstead collection today, is a beautiful azurite that grew these huge azurite crystals over older malachite pseudomorphs after azurite. So it's these stories that get me excited about Bisbee, um, and hopefully you too. The ones at the bottom, the azurite on the left is probably my favorite single azurite specimen. This is more than a foot wide. I don't know the exact dimensions, part of the Graham collection. And the cuprite, my nickname for the cuprite in the middle is the Jolly Rancher. And that's probably the world's best cuprite, also part of the Graham collection found in Bisbee. And then just another malachite and azurite, so showing boxwork texture. In addition to these copper carbonates and copper oxides that you see there, Bisbee's turquoise specimens are also part of this supergene mineralization that has happened during one of these erosional events. And most of the Bisbee turquoise comes from one part of the district. The The ones on the left here, this large one on the bottom left, just to give you an idea how large that specimen is, this is it right here. If you can see in the picture, it's about 8 inches across or so. And the red matrix is part of the glance conglomerate. And the two, or actually the three surrounding it, are all part of this turquoise that formed in a glance conglomerate. And we're going to talk about how that formed and what it means. But the neat thing is, most of the Bisbee turquoise comes from this one occurrence. There are two other occurrences that I know of, and those are the two images to the right. The top right, the 1200 level of the coal, that's a small specimen, maybe 6 centimeters in length at the max, and a small little discontinuous turquoise vein in an igneous rock. Um, that turquoise from that locality, it didn't produce very much, very few specimens, and not really of lapidary quality. So we won't discuss that further. And the same thing with the one on the left or the bottom right, the 1400 level of the Dallas. This is a vug with turquoise and cuprite. This is Chris Whitney Smith specimen, and these would have never made cutting grade or lapidary grade turquoise. So those are fantastic specimens, but not part of what made Bisbee famous as far as turquoise and turquoise jewelry. So how did the Bisbee turquoise form? And this is a picture of the lavender pit. And what you notice, what's outlined in red here, is a paleo channel that formed after the deposit was formed. So the deposit came in at 200 million years ago. On the left-hand side here, we're basically looking right down the lavender or right down the dividend fault. And so this whole section here has dropped more than 1,000 meters downward with respect to the footwall, which is across off the picture to the left. And as there was erosion happening, there was a paleo channel that deposited this Cretaceous glance conglomerate in this region. And they started mining the lavender pit, pre-stripping it around 1950. And previous to that, Bisbee had not produced any turquoise. They, in fact, didn't know the turquoise was there, and it wasn't until about somewhere between 1951 and 1953 when they were getting down towards the lower parts of this paleo channel in the glance conglomerate that the Bisbee turquoise mineralization was found. And the turquoise was never mined as ore. They actually piled most of it up on the number 7 dump. So they were pre-stripping the pit to get to the ore, and this turquoise was not considered ore. In fact, it became kind of dangerous because the integrity of the rock here was very, very dangerous. Loose soil, always caving, and during pre-stripping and stripping of the pit and mining of the pit, it was pretty much off limits to collect the turquoise. So most of the turquoise went to this dump right here. So this old photograph on the left, part of the Graham collection, this is the beginning of the number 7 dump right here. And this, where my mouse is, this here would have been where the Sacramento Hill would have been. And this is the old Sacramento pit. The town of Bisbee sits up here in the valley. And the Junction mine is right here. So all this today is pit. But when they were pre-stripping it and including the turquoise, most of it went to this dump down here. The photograph to the right is now looking towards the number 7 dump from Queen Hill, and so we see part of the pit here called the Holbrook Extension, the main part of the lavender pit, and then here's the Junction shaft. So it's in this area that this paleo channel. And so all the turquoise that's been produced in Bisbee of cutting grade is pretty much from this region here. And it's now most of it is stacked up on this dump. So during this stripping of the pit, there was a little bit of material from this glance conglomerate that was temporarily put in a mine dump, backfilling the Sacramento pit. Well, over time, that when that part was mined, they thought, oh, at first that what they were encountering, hey, there's turquoise here. But it clearly became evident that no, the turquoise is only there because it was stacked up in the pit in the earlier Sacramento pit. Really, the only turquoise from Bisbee comes from this area, with exception to those two minor occurrences that we talked about earlier. All right, so now what we're going to talk about is provenance of turquoise. So, what how do we characterize the turquoise? Because each deposit has its own signatures. And historically, most of the turquoise has been looked at for trace element analysis, and that's once again for the archaeological context. And so it started in 1975 with some crude instruments, atomic emission spectroscopy and neutron activation, where people started to look at trace elements in turquoise. To me, one of the most important studies is this one from 2015. Alison Thibodeau, she was here at the U of A, and she looked at the turquoise and looked at strontium and lead ratios, and that's what these plots to the right are. So looking at strontium ratios here or lead ratios, and Allison basically looked at a whole bunch of different deposits. So all these deposits from Mineral Park to Gleason to Morenci, to other places in New Mexico and Nevada, and characterized them and noticed that in regions, you could really break out different regions by their strontium ratios or their lead ratios. And while it doesn't work across all deposits, it gives you an idea that, hey, we're learning something about this turquoise, and we can tell differences from things from, say, Gleason and Mineral Park. They look different than Oro Grande and King Mine or Cerritos, that sort of thing. So can really tell differences in the turquoise from far uh, apart deposits. Um, and then since then, in 2023, Tong et al. Looks at 48 elements as well throughout a lot. All these are basically for archaeological context. Well, here at the U of A, in our research group, we wanted to think outside the box because we wanted to characterize Bisbee turquoise itself. And so we started with specimens that the Grams uh, had given us. The one on the top is a glance conglomerate sample, and the one on the bottom is a glance conglomerate with turquoise. And what we thought of, let's actually, instead of looking at the turquoise, let's look at the matrix because the turquoise all comes from one area. You have to have certain conditions to grow this turquoise. The copper has to be there, the aluminum, the phosphate. And so most of the turquoise from a locality has the same host rock. And in this case, it's the glance conglomerate. So what we do in the lab is we do detrital zircon geochronology. And so we took a couple control samples, that's A and B on the left. And we also took a vein sample from a turquoise that I had purchased from a collection and was told that it was Bisbee, but there's no proof. So I ran that one as well. And why why did we run it? What we ran it for was called the detrital zircon geochronology. And the premise is we're gonna sort of talk about how this can form and detrital zircons can get in a system and then how we can use it. So the top photograph would be mountains. So here in the North America, it could represent the Rocky Mountains, the Appalachian Mountains. And as those mountains are uplifted and eroded over time, they produce sediment. And in that sediment would be this picture. This is a picture of a hundred or so detrital zircons. And so zircons are zirconium silicate that when they form, they incorporate a little bit of uranium. And we could use that uranium and date it to determine the age of that particular zircon. So in a system that came from the Appalachians and then mixed with a river that came from the Rockies, well, you could have a mixed signal in here, and that's what happens. And so as time goes on, these rivers, this Ron Blakey paleogeographic map shows time in the past where you had different river systems contributing sediment to here in the southwestern North America region. And then all that sediment is deposited in some sort of fluvial system, some sort of river system or deltaic system. Here in Bisbee, that's what the Bisbee Glens conglomerate is. It formed in that paleo channel, and it looks just like this one, where you had the sediment that holds these zircons. Um, and then time goes on. And as time goes on, the supergene mineralization happens. And in this Bisbee Glens conglomerate, you had areas that formed turquoise. So the turquoise either replaced single pebbles, it either coated the pebbles with a small rind, or there was some open space filling in these quartz veins, and the whole open space of the quartz vein filled with turquoise. And all of that happened here in Bisbee. And so we take those rocks, we separate the little zircons out of them, and this is what I do every day. So I take it for granted that you'll know what we're doing, but we use what's called laser ablation ICP mass spectrometry, and the photograph is one of our mass spectrometers and a laser. So the dark instrument here is a laser, and inside that laser, we put one of these pucks that has thousands of zircons mounted in it. And then we hit that surface. Each individual zircon is somewhere about 150, 200 microns across. So about the diameter of a human hair. And we drill with a little light, essentially a little light jackhammer that ablates the crystal. And so we start ablating the crystal, boom, 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 and we excavate material. And we carry that material through this little white line that goes into the mass spec. And at the mass spec, we have this thing that's a plasma. And that plasma does something magic. It strips electrons and off the material. It's called ionization. And then that little amount of material enters a vacuum. And then it enters the vacuum into the mass spec. And the mass spec then does what mass specs do. It takes those positively charged ions and separates them with a magnet, and then we measure them. And so what we could do is simple isotopic ratios to determine the age of this grain, this grain, this grain, this grain, until we're at a number that we're satisfied with. And why does this work? And it's because of uranium decay. Basically, uranium-238, the top graph here, uranium-238 decays to lead-206. So when a zircon forms, it incorporates a little bit of uranium-238. And then through radioactive decay, through a series of what are called alpha and beta decays, it decays through a whole bunch of different mineral or different elements, and it ends down at lead-206. So if we measure uranium-238 and we measure lead-206 and do that ratio, we put it through an age equation, we can basically tell the age of that crystal. Well, I won't get into it, but there's another decay system, uranium-235, that decays to lead-207. There's also thorium-232 decays to lead-208. And we use all of these to determine the ages. And here's what we found. So this graph on the left is what's called a probability density plot. And this is going to create allow us to create a signature. So we know that if we look at if we have a sample of turquoise and we look at the matrix, we know what like what it should look like because of what we've done. So on the x-axis, it's age. So we build these one at a time. The first one, the green PDP, is built one grain at a time. One age at a time goes in there, and collected 195 analyses, and we see there was a peak of ages from rocks that were about 1.6 billion years old, and then a couple others all the way down to about 1 billion years old. And then there was another cluster in the Paleozoic around 500 million years ago, and then another cluster during Jurassic time about 200 million years ago. So um, we ran a couple Bisbee turquoise or glance conglomerate samples, and that's what we found. And then we did the one that I wasn't sure that was from Bisbee or not, but I suspected it was. I couldn't get as much material because this is a single vein of turquoise. This is actually the piece right here. Uh, and so there's still a little bit of matrix, but I just cut off a little bit of matrix. And even in that little bit of matrix, we found 61 zircons. And sure enough, we get similar patterns. Um, the pattern that matches this area, the pattern that matches the 500 million year old ages and the Jurassic ages. And so by combining these three, we now have a signature of what the matrix from Bisbee turquoise looks like. And that's this BGC composite on the bottom. And so we wanted to compare that to some other areas. Um, Real quick, I'll sort of show you what that means. This is one of the PDPs with the ages listed in numerically, and you can see we know this is from North America. The 1.6 billion year old grains. If you look on this map, this is a basement geology map of North America, and that's part of the Yavapai Mazatzal terrain. And sure enough, that's the basement rock in Arizona. So this light purple, that makes up this 1641 peak. The 1459 peak, that's made up of zircons that eroded from all these little stars that also deposited in the glance conglomerate. That's from what are called the anorogenic granites. That's this magmatic province, 1.34 to 1.48. Same thing with the 1.2s. That's part of the Grenville orogeny. Those sediments and zircons come from this blue line. The same with the 1.0s. The 500s, those we weren't actually sure about exactly where they come from, but there are some Amarillo, Wichita province, and also in New Mexico that there are some 500 million year old zircons. And then we know we're in a Jurassic arc. So this 200 to 176 peak, that's from the Jurassic arc. That's from the rocks that actually formed the deposits at Bisbee. And so we decided to do the same test on two other samples that look like Bisbee turquoise. So we took a sample from Kerman, Iran. This blue from this locality looks very much like Bisbee blue, and we did the exact same process. And when we plotted on a PDP, you see it's unimodal. There's only one peak, so it looks completely different than Bisbee turquoise. And we knew this would be the case. This is a slightly different type of matrix, but the Bisbee blue looks the same. And it turns out that the rock that this turquoise formed in is as young as 14 million years old. So it's exactly 13.81 plus or minus 0.14 million years. So it looks completely different. We also did the same thing for Mongolia and did the Erdenet turquoise. This is the actual sample here. Once again, when it's polished, it looks just identical to Bisbee turquoise. This comes from a Triassic deposit, and it also is unimodal. So the peak here is one peak at 237. So if we have matrix with turquoise, we can tell where it's from, at least from one of these three deposits. This was the preliminary study where we started with just three. We're now doing it on all the turquoise throughout the world. But For these three, it shows a good example that here's that the PDP comparing these three. The star is what Bisbee turquoise looks like as far as the detrital zircon age spectrum. And the next one down, Kerman, Iran, that's a single peak, very young at about 14 MA. And then Erdenet is a single peak, maybe a slight little older blip in there as well. But it's clear that if we have matrix, we can distinguish without a doubt where the turquoise comes from if we're looking at these three localities. Stay tuned for once we have the rest of the localities in North America completed. So that was the first part of the study, and that's the part that Gabe, the student, helped with, and he presented or he's going to present some of it at the Tucson Gem and Mineral Society show this year, this coming February. The second part that we wanted to work on was actually looking at isotopic ratios in the turquoise itself. And this is what Jason Kirk helped me here with at the U of A. And the bottom right picture is the instrumentation that we used to look at the isotopic ratios of turquoise and variscite from Bisbee and elsewhere. So the black box here is the laser, and then this is the mass spec. Different type of mass spec, but does similar isotopic ratios. And what we did is we took veins of turquoise. So that vein of turquoise that I had, we actually sliced it and then rastered across it with the laser. And as we rastered across the turquoise, we actually realized, hey, we're seeing something amazing in this turquoise. We can actually see how the turquoise is growing and do maps. So the image here on the left is the turquoise, the lighter blue here in the map, that shows where we took the analyses from. And then the results are off to the right. And you can see the uranium lead, the parent daughter ratio is different based on where you're at in the turquoise. So we got really excited about this. And it turns out that this is what we found out. So if you do what are called pseudospot analyses, I won't get into all the minutiae of the analyses, but we can actually tell that the inside of the turquoise vein, that's the plot to the right, where we regress a line through all of the analyses and come up with an age. It looks like the turquoise on the inside of the vein grew at 5.4 MA. And that was after the plot on the left, that just shows the upper section. And when we regress a line through that, it shows that the outer part of the turquoise grew at actually 7.4 MA. And the neat thing is, what happened here in the Southwest at that time? Well, the Gulf of California began to open, and that affected monsoonal patterns here in the Southwest, right at 6 million years. So right at the juncture, as this turquoise vein was growing, the Gulf of Mexico was opening and the monsoons were changing here in the Southwest. And so it's those sort of relationships that I'm excited about, that we're learning more from a piece of jewelry, essentially. And this is a little video of the turquoise. So this, you could just pay attention to all the bars. I'm going to play it. And this is how the turquoise grew from the outside of the vein to the inside of the vein. And that was generated by these pseudo spots. So if you want to learn more, send me an email, come visit the lab. I'd love to show you around. Well, but bottom line is just to show that we could do this for other places. We did it for Erdenet, Mongolia. It turns out that we remember, this is the one with the rock is 237 million years old. Well, we know the turquoise has to be younger than that. Well, it grew at 110 million years, different than Bisbee. The one from Iran, remember, this host rock is only 14 million years old. So we know that the turquoise, that supergene, had to have formed younger than 14 million years. Well, it turns out that it's growing right now. It basically grew And the age that we got is 2,000 years plus or minus 560,000 years. So regardless of where we're at, we can now zap turquoise and actually tell the age of the turquoise and where it's from. We did this for a couple other supergene minerals in Bisbee. Turns out variscite that also grows uh, or grew during the same time frame. We had a couple samples of variscite. They also dated to 7.4 Ma. So this was a big time of erosion and deposition of minerals down around the Lavender Pit. And then this is the last one that I'll show. This is a Bisbee variscite from the 1200 level of the coal. And everyone in the mineral community thought this variscite was primary in origin or hypogene. And so that would have meant that it was about 200 million years old. Well, after running our analyses, that's clear that's not the case. It also formed about 7.1 million years old. And so it just filled a crack in these sulfides. So lots of fun stuff going on here. The bottom line is we found that if you have matrix, we can characterize where your turquoise from. If you don't have matrix, we can hit it with a laser and do uranium-lead geochronology and find out where it's from. And yeah, the neat thing is we're relating these results back to tectonic events and paleoclimate and yeah, exciting stuff. This is our next chapter. We're in the process right now of running turquoise. I have some more students working on different turquoise localities. I'm still looking for certain localities. When we do localities, we have to make sure that we have material that has matrix that also comes from the specific deposit that we're looking to characterize. And so we're in the process of doing these others now. Last two slides are, hey, Bisbee's mining future is possibly still ahead of us. On the one side of the Lavender Pit, you'll see all those red rocks up in the hills. That's part of the Cochise deposit. Those are unreactive rocks, not like the limestones that are on the other side of the Dividend Fault that have been mined. So because they're unreactive, it's not likely we're going to hit minerals at the same amount or beauty as that you saw in those reactive limestones, like the azurites and malachites and the turquoise. But undoubtedly, they'll find some if that ends up being mined. But I think there's still one more chapter of mining left in Bisbee, maybe. And then also, I just want to leave you with, for those of you who have not gone to Bisbee, you have to go. It's an amazing place. The museum houses a world-class mineral museum, and the history. You'll learn more about the history of Bisbee than, yeah, well, it'll be unbelievable. And then the mine tour. They still do the mine tour going into, it says the Queen Mine 1915 there, but it actually is going in the Southwest Mine. But it's in the mine the same rocks, and you'll be able to get to see part of the original Copper Queen decline. So go to Bisbee, have fun, and that's pretty much it. I'd love to answer questions if there are any.
There sure are, Mark. That was fantastic. Thank you so much. Our
No
first
problem.
question is from Barbie. She asks, in her many visits to Bisbee, that she was told there is no Bisbee turquoise available in Bisbee nor anywhere else. And then imagine to her surprise when she walked into Gemstone Galleries in Santa Fe, New Mexico, and there she found a case of Bisbee turquoise. The owner, Peter,
Oh, you were cutting out there. Hopefully you can still hear me.
oh, yes, I sure can.
Okay, great. Yeah, I think that's pretty typical. That is correct. There is no market, like there is no active mining of Bisbee turquoise. It's off limits. You cannot go and collect Bisbee turquoise. There is still turquoise in the mine dumps that maybe someday Freeport McMoran, who owns it, will do something with it. But at this point, there is no way to go supply new Bisbee turquoise. So it's just what is out there in old mineral collections. And the crazy thing is, the mineral collectors who collected all the azurites and the malachites, they actually turned their nose up at the turquoise because the prices from the lapidary community were driving up prices, and they couldn't spend or didn't want to spend, couldn't justify spending real money to pay high prices for turquoise when they could buy a beautiful azurite or a beautiful malachite pseudomorph after azurite and things like that. So a lot of the Bisbee mineral collections don't have really spectacular turquoise specimens. So they are hard to find. Anytime I come across one, I can afford it, I pick it up if I can. And occasionally you will find places that have it. But just always, if the rock, if if the rock is available with the turquoise, look at the rock. It should look something like this. It's typically a red hematitic cemented breccia, and that's part of the glance conglomerate.
All right. Our next question is from Stephen. He asked, is it safe to say that Bisbee blue resulted from geologic history of North America's river system and the deposits from that channel in the Lavender Pit? Other turquoise samples had simpler geology? I think you answered a little bit of this before his question.
Yeah, wow, that's a great question. Certainly, the local geology had played into it. Even in the glance conglomerate, some of the turquoise is almost white and very chalky and not very hard, and a lot and some of it is this grade, and some of it's a little bit better, more that grade. So you even within a deposit, the turquoise does vary, and it's to your preference. But there are other places that produce similar looking turquoise, um, and that's part of the reason that I wanted to make sure that we can figure out and do it with some sort of quantitative analysis that we can say, hey, yeah, this is definitely from Bisbee. This is not likely Bisbee. It's likely from this deposit or that sort of thing.
And has this particular research you performed on Bisbee turquoise, has it been published yet? And if it has been, where can we find it?
Yeah, yeah. It's written up, and basically it's not actually out yet, so you're getting a glimpse into it. But it's going to be a series of a couple papers. So the first one is just the three localities that we talked about in this presentation: Bisbee, Erdenet, and Kerman, Iran. And then I'll let you know once it's out. Hopefully in the next couple months. And then the second paper is a more comprehensive on the rest of them here in the Southwest. So it includes turquoise from Nevada, Colorado, New Mexico, Mexico, and Arizona. So they're coming. We're not quite as fast as I'd like to be, but yeah, almost there.
And then a question that I have is after you finish your study with turquoise from around the country and potentially the world, um, will you be looking at other Bisbee minerals? Then I ask this because I have occasionally been tricked before holding a specimen by Chinese azurites.
Yeah, well, you're not the first person to ask that question. And I gave this presentation to at one of the Arizona Mineral Symposiums, and Les Presmick said the same thing. He wants to know when we could do it for azurites and malachites. Well, we have tried. There, so at this point for azurite, it does not look possible. And we knew this. There is no, well, let me step back a little bit. There's a reason that zircon and turquoise take in a little bit of uranium when they form. So these phosphate minerals, the charge and the ionic radius allow substitution of uranium into the crystal lattice. So zirconium is like a +4 charge, and uranium substitutes for it. So we know exactly where the uranium is going to sit. With these other minerals, there's no space. But in Bisbee, there's a lot of uranium in parts of the deposit, which is unique to Bisbee. So it's the perfect study place to find these other minerals that might do it. But the uranium's not going to sit in a specific site. It's going to sit somewhere else with between bonds, or it depends on the mineral. Well, it turns out we tried with azurite, doesn't work. We tried with malachite, typically doesn't work. And then we found one malachite that it does work a little bit. So stay tuned. Certainly calcite, we can do the exact same type of measurements on calcite. So Bisbee does have a lot of calcite that will be one of the minerals we work on as well.
That's exciting. That's exciting. No pressure.
Yeah. There are others though. Yeah.
Sean has said that he finds lots of veracite in Bisbee on his rock hounding tour from an old trail where he believes that the coal shaft tailings were dumped. And sometimes it has some blue, but mostly minty green, but not much pyrite for matrix, where there are other veracite locations, or were there other veracite locations?
Yeah, so the lavender pit produced quite a few. The varicite that comes from the lavender pit are often in nodules, and so if I go back just a couple, this photograph here on the bottom right, these all come from the lavender pit. They're all varicite nodules, and yeah, those all grew somewhere about the same time that the turquoise was growing. In fact, there's a new mineral, metavaricite, in one of these nodules that we've dated as well, and that dates from a similar time frame. And that's going to be a newly reported mineral for Bisbee. But so two places that I know of in Bisbee, the Lavender Pit, and that includes the Holbrook extension of the Lavender Pit, and then the coal mine. The varicite does look different. The Lavender Pit ones are typically nodule, like the photograph you see, and then the ones from the coal are typically like this, where they're in hypogene sulfides.
And these studies that you're performing, I know that you said you had a mini jackhammer with the laser. Are
Yep.
they all destructive testing and that you've been doing or not?
Yeah, but they're destructive, but barely. We've done gemstones, and we drill little holes into the back of the gemstone, and you cannot see it with your eye. To give you an idea on how small we can go down to 10 microns. And so if you take a human hair and you cut it in half and you turn it on edge, we could probably fit 10 to 15 um, laser pits in the end of that human hair. So these are very tiny little spots that we're ablating the material out of. So even on a gemstone, you don't see it unless you're under a microscope, then you can see it.
Wow, this has been a fantastic presentation. Thank you so much for your time today, Mark. And I also want to make sure that I thank your research partner. I, Gabe, Jason, as well as Richard and Doug. I do know that Richard Graham III would be extremely pleased with the scientific research surrounding Bisbee. That was one of his dreams, is that scholars such as yourself would find out why and what makes Bisbee so interesting and unique. And you are a part of that. And he would just be thrilled.
I love to hear that. That makes my day. I will say this whole study ended up, well, as you know, is because of uh, your father, and then my conversations with Doug and also Richard. I remember clearly the day Doug, we were in the Copper Queen mine tour talking about um, all the Bisbee turquoise, and it was his recommendation. He said, "We got to figure out how to do it." Well, we're figuring out how we do it. So it's been fun, and I really owe a lot to all of them.
Well, thank you so much, and thank you, audience today. And if you've missed any part of this program, as I said at the beginning, a link to the recording of today's program will be sent to all of our registrants today. And with that, I'd like to one last time, Mark, and thank our audience. Have a great day.
Thank you. Bye bye.